Good morning, and thank you all for your assistance to the presentation of this paper. My name is Esteban Brito, and today I'm going to present the results of our work in the task of selecting interpretation techniques for an image classification use case. This project is product of the collaboration between the Instituto Tecnológico de Mérida, the Universidad Complutense de Madrid, and the AAAI Student Chapter Mexico. If you look at the bottom right corner of the screen, you'll see that the slides are numbered, so you can refer to them at the end of the presentation if you have any questions. Having said that, let's begin. Let's introduce the main problem this project solves. In the artificial intelligence field, there are many models and algorithms that mimic the human behavior in certain tasks, such as classifying objects in images. However, we need these models to not only be accurate, but explainable. Many explanation techniques exist, but in the image classification field, these techniques should answer one question. Why was an image classified this way? So, if an image was classified as a zebra, the technique should generate a visual explanation highlighting those areas that contributed the most towards classifying that image as a zebra. Keep in mind that several techniques exist, and they generate visual explanations in a very different way. So some techniques are more suitable for certain images. Deciding which technique should be used for a specific image is a problem on itself. This problem was addressed in a previous work by the authors of this paper, using a case-based reasoning approach to determine the most suitable techniques for images classified by a neural network. Through a voting process held by a group of users, you obtain a case base where we could identify the most suitable techniques for many images. And to predict techniques for new images, we looked up which techniques were most suitable for similar cases. However, this process is not scalable to large case bases because during prediction time, similarities have to be calculated between a new between a new image and all the cases in our case base. To overcome this issue, a new hypothesis has been proposed. We already know that in a CBR cycle, similar images should share similar solutions. But what if the clusters of similar images could be aggregated to produce a smaller, curated case base? That is the clustering hypothesis. Or, in other words, that clustering can be used to optimize a case base, reducing prediction time while still maintaining a good prediction performance. Let's see a bit of content about the theory used in this paper. On this paper, 4 interpretation techniques were evaluated. These produce different visual explanations and generally function in a very different way. Some of them, like Lime and anchors, are model agnostic techniques that make perturbations to the images they want to explain. Others, like integrated gradients or X-ray, are model-specific techniques focused on computing attributions. The exact inner workings of these techniques can be consulted in our paper. Now, if you want to cluster cases, we need an algorithm to do that. dbScan is a density-based clustering algorithm that generates clusters in a simple fashion. Using the m and epsilon parameters and given several instances or points in space, dbScan recognizes 3 types of instances. Core instances that have at least m other instances within epsilon units of distance, and they are considered part of a cluster. Border instances that are close to core instances, and all the remaining instances, which are also called noise instances. They are not part of a cluster. Now that we've explained the theory behind the project, let's get into the methodology that we developed. The dataset utilized to generate our case base is composed of 200 images taken from the Visual Genome Project dataset. The exact selection criteria for these images can be consulted in our paper. As mentioned before, a voting process was held to determine which technique was the most suitable for each image. Here, we see a picture of the web interface the users employ to select visual explanations. However, instead of focusing on highlighting only the most suitable technique, we've decided to associate each image with a vector of 4 elements, each one representing how many votes every technique received by the users. These vote vectors are described like this. The first element describes the votes received for the Lime technique. The second element describes the votes for the anchor technique, the third for the IG technique, and the fourth for the X-ray technique. After the voting process, the cases can be properly formalized. Every case is composed of a description and a solution. Each description has 3 alternative representations: an image pixel matrix, a color histogram vector, and a latent features vector. How these alternative representations were generated can be consulted on the paper. Also, each solution refers to a vote vector like the one we described before. This case base will be referred to as the original case base from now on. According to our clustering hypothesis, similar images should cluster together. Clusters share different features depending on the representations and metrics employed during clustering. In the screen, for example, we're using pixel matrices as image representations. When we look to the cluster inside the red circle, we see that descriptions and solutions from these 3 cases can be aggregated into a representative prototype of the cluster. This allows us to create a new case base, referred from now on as a prototype case base. Each prototype case is composed of a description and a solution. The description contains the aggregated descriptions of every case inside its cluster. The aggregation uses an averaging function for each description component. So, for example, when processing these 3 images, our function should calculate 3 prototype description components: an average pixel matrix, an average color histogram vector, and an average latent features vector. The solution part of a prototype, on the other hand, is the average of both vector of every case inside a cluster. If we average the both vector of these 3 images on screen, for example, we get a prototype solution. As we mentioned before, clusters are generated using different representations and metrics. On the table below, we introduced the concept of similarity IDs, which are basically combinations of image representations and similarity metrics. Observe that some metrics can only be applied over certain representations, like structural similarity, which is only compatible with pixel matrices. Also, not all similarity IDs produce valid clusters, or in other words, clusters that can be used to extract prototypes. In the table below, we present all the dbScan parameters that generated the best clustering results for each ID. However, the SSIM ID results are blank because it did not produce any valid clusters for our case base. A detailed explanation of this table can be consulted in our paper. Once the different cluster case bases have been constructed, we can explain how the CBR cycle works. When processing a new query image Q, the retrieval stage of our cycle finds the k nearest prototypes to Q. In the example, k equals 3, but the number can vary. We'll see that in our evaluation phase. These nearest prototypes will be utilized to generate the prediction of our CBR process. The reuse stage aggregates the solutions of the nearest prototypes using a numerical average. So, the 3 vote vectors on the screen are numerically averaged to get the vote vector predicted for a query image. Knowing how many votes would have been casted for an image provides the user with the possibility of selecting as many techniques as he or she wants to explain this query image. In our example, both the first and third techniques present a relevant number of votes, so they should work well in that task. And also, The accuracy of this process can be measured computing the root mean squared error, RMSE, between predictions and real bot vectors. But our method does not hold any value if this does not work. The CBR approach needs to fulfill two conditions. First of all, that prediction performance shown in our new CBR process is similar to our previous CBR system, and that technique selection time is smaller than in our previous system. Regarding prediction performance, this condition is fulfilled. In the graph, colors indicate different similarity IDs. The solid lines represent performance of the new prototype case basis, and the dashed lines, the original case basis. As the number of k grows alongside the x-axis, we see that there is no relevant difference between them, meaning that they both share similar capabilities when generating predictions. This equality, however, does not hold in the time performance graph. Here, we plot the average time each case base takes to generate a new prediction, using different numbers for k2. Prototype case bases have the upper hand here, because their time are significantly smaller than the ones presented in original case bases. This is due to the reduction of the number of instances in the prototype case bases. When trying to find the nearest cases, the process has to calculate similarities with a smaller number of them, and so predictions takes less time. This leads to the following conclusions. First, that the clustering hypothesis still holds, meaning that clustering can be applied to optimize a case base used for selecting explainability techniques for image classification. Also, that there's no significant difference in performance prediction between case bases. And most important of all, that query times are reduced up to 10 times when using optimized case bases. Several improvements can be made to the CBR process. We could compare more than just 4 explainability techniques, for example. We could use more similarity metrics and image representations. We could use more clustering techniques than just dbScan, of course. We could also include more images in our dataset. And although clustering is useful for optimizing a case base, we still don't know exactly how or why it does it. In that regard, there's an ongoing work using PCA to make our clustering approach explainable. And that's all. Thank you for your time and attention. And if you want to contact us, please use the information on the screen. Have a nice day.